Good evening. I'm Spot On Weather meteorologist Matthew Euler, and today we're going to take a look at the next topic in the summer weather video training series, and we're going to cover the climate. An easy way to remember what climate is, or the difference between climate and weather, is climate is what you expect, whereas weather is what you get. So let's roll right into the training. The first thing I'd like to do is describe kind of a few definitions here, mainly about the science of climatology, where climatology is basically the scientific study of climate. And climatology is a tool, and it's used to develop long-range forecasts. So forecast models are only going to be really accurate out to a certain amount of time into the future. And beyond that window is where climatology, or the average weather or average temperatures and precipitation for a location on Earth, that is generally going to take over from the model forecasts to paint a picture of the weather at a location. And usually when we look at climate generally covers the past climate. We look at the past 30 years in general. Now there are three principal approaches to climatology, or the study of climate, and these include the physical climatology, descriptive climatology, and dynamic climatology. For physical climatology, this is seeking to explain the differences in the climate in light of the physical processes influencing climate and the processes producing the various kinds of physical climates, such as a marine climate over water or the ocean, a desert climate, or the mountain climate. Now, physical climatology is going to deal with the explanation of climate. Descriptive climatology, on the other hand, orients itself in terms of geographic regions. It is often referred to as regional climatology. It's a description of the various types of climate that's made on the basis of analyzed statistics from a particular area, like the mean temperature, which would be mean referring to average temperature for an area, what you'd normally expect for average precipitation for a region. Attempts to describe the interaction of weather and climatic elements upon the people and the areas under consideration. And descriptive climatology is presented by verbal and graphic description without going into the causes and theory. And finally, there's something that's known as dynamic climatology. This attempts to relate characteristics of the general circulation of the entire atmosphere to the climate, tying in those two areas. And it's used by theoretical meteorologists and addresses dynamic and thermodynamic effects. So there's three types of climatology we talk about: physical, descriptive, as well as dynamic. All right, so now let's move on to a topic that's known as climatic elements. Now these elements include temperature, precipitation, the average wind direction, and speeds for a particular location. The first element, temperature, is going to be dependent on the latitude on the Earth. How far north or south? How far are you in relation to the equator, 0 degrees latitude, versus, let's say, the Arctic Circle at 66.5 degrees latitude, or the North Pole or the South Pole at 90 degrees latitude, right? So temperature is going to be dependent on that latitude or the distribution of incoming and outgoing radiation. We look at how high the sun is, that Earth-Sun relationship for a specific latitude. The nature of the surface, land versus water. The altitude, how high up and off the ground is the location, for example, in a mountainous area. That impacts the temperature and the prevailing winds overall. The moisture or lack of moisture is going to play a significant role in modifying the temperature. The more moisture in a region, you're going to have a smaller temperature range, and the drier the region, such as a desert, you're going to have a much greater temperature range. Now, moisture is influenced by temperature. I mentioned this in previous training videos that warmer air can actually hold more moisture or water vapor than cooler air, resulting in increased evaporation, as well as a higher probability of clouds and precipitation. And a great example of this would be in certain parts of the tropical areas where we get that belt of converging winds known as the intertropical convergence zone, where it's a discontinuous belt of thunderstorms. Precipitation. So we talked about temperature. Now we're going to move into the precipitation discussion for this element. It's defined as water reaching the Earth's surface by falling either in a liquid or a solid state, either or, and its most significant forms are going to be both rain and snow. Precipitation has a wide variability over Earth's surface, from scarce amounts over the desert areas, there's even scarce amounts over the polar areas, to an abundance of moisture in the tropical areas of the Earth. And precipitation is usually expressed in inches in the United States. It may be expressed in other units, such as millimeters, overseas into Europe. So the units do vary, but in the United States we do use inches for our climatology. Wind, that is the climatic element that transports both heat and moisture into a region. Climatologists are mostly interested in wind. They're mostly interested in that wind with regard to its direction, its speed, as well as its gustiness. And wind is usually discussed in terms of prevailing direction, the average speeds, as well as a maximum gust for a location. If I were to look at the climatology of a specific point or station on Earth's surface, and I'm looking at wind, that's what I'm looking for. How much time of the year does the wind come from a colder direction in the northern hemisphere, such as the north, versus a warmer direction, the south? Stuff like that. All right, now we introduce you to these climatic elements of temperature, precipitation, and wind. Let's now turn our attention to these climatic zones. Now, Earth is classified into 5 broad belts of climatic zones. These are based on astronomical or mathematical factors. The zones of sunshine or solar climate, where you have a very high sun year-round, this is going to be known as the torrid or the tropical zone. And then between the tropics and the polar areas in both the northern and southern hemisphere, there's going to be 2 temperate zones, one in the northern hemisphere, one in the southern hemisphere. And then you're going to have 2 polar climatic zones, one in the northern hemisphere, one in the southern hemisphere. So let's break down these climatic zones a little more in detail, describe their boundaries. The tropical zone is going to be located basically between the Tropic of Cancer, which is at 23.5 degrees north latitude, and the Tropic of Capricorn at 23.5 degrees south latitude. That's the tropical zone, also known as the tropics. If you were to look on a globe, you would generally see some key latitude reference points. You would see the equator at 0 degrees latitude. You would see the Tropic of Cancer at 23.5 degrees north latitude. You would see the Tropic of Capricorn, there'd be a line on that globe, at 23.5 degrees south latitude. And then there would be the Arctic Circle and the Antarctic Circle at 66.5 degrees north latitude, as well as 66.5 degrees south latitude. And then there would be the North and South Pole, which is North Pole's at 90 degrees north latitude, South Pole at 90 degrees south latitude. Now the temperate zones of the northern hemisphere, those are generally going to be located between that Tropic of Cancer at 23.5 degrees north latitude and the Arctic Circle at 66.5 degrees north latitude. The United States is within that temperate zone. And then those 2 polar zones are located between the Arctic Circle, 66.5 degrees north latitude, and the 90 degrees north latitude. Now, climatic zones can be classified by these isotherms, or lines of equal temperature. Isotherm, iso meaning equal, therm meaning temperature. Now, the sun is going to pretty much transition its journey between the Tropic of Capricorn at 23.5 degrees south latitude. That's its furthest southern point. And then the furthest northern point for the sun is going to be at 23.5 degrees north latitude, the Tropic of Cancer. So every year, the sun is going to travel between those 2 latitude lines. And so that whole area between those 2 points is known as the tropics. All right, so if we look at the climatic zones and looking at a map, and we use those lines of equal temperature, or isotherms, the polar zones are generally defined by areas that are, the warmest month is 50 degrees Fahrenheit. That's the warmest it gets. If I, for example, go to the North Polar Zone here at the top of this diagram, all locations north of that 50 degree Fahrenheit isotherm are going to be colder than 50 degrees year-round. It won't get warmer than that. Then we have the boundary of the southern boundary of the North Temperate Zone is going to be sitting at the mean annual isotherm of 68 degrees. And then between the 68 degree Fahrenheit isotherm lines, we have the hot belt or the tropical area. So this is a great look to just kind of see how we use those lines of equal temperature on average throughout the year to determine the climatic zones. All right, now let's take a look at the climatic types. Now, there are 3 classifications out there of climate, and those include the CW Thornweight, the W Koppen, and then the GT Trewartha. Now, the Koppen, I don't have the 2 little dots above the O in Koppen, but generally these are the 3 types of climates classifications. Here are the differences. So Thornweight, he places his emphasis on effectiveness on precipitation and evaporation at a certain location. He classified climates into 8 main climatic groups, with 5 groups focused on precipitation and 3 climatic groups based on temperature. Koppen classified climate into 5 main climatic types: tropical rain, dry climate, warm temperate, rainy climate, cool snow forest, the boreal, and polar climate. Those are the 5 zones that are classified by Koppen. And he based those types on temperature, the precipitation amount, as well as the season of maximum precipitation. So what time of year does a location get the most precip? Trewartha, on the other hand, Trewartha divided climatic types based on Koppen's classification. However, there are significant changes that have been introduced, forming 6 climatic groups under the Trewartha climate classification. These include tropical, dry, subtropical, temperate, boreal, and polar. Now, 5 of these groups are based on temperature, and 1 of those groups is based on precipitation. So a lot more emphasis on temperature for the Trewartha classification. So those are the 3 main climatic classifications. Those are the main differences between Thornweight, Koppen, and Trewartha. So if you take a geography class and do a little world climate, you'll probably hear about these folks and the climate classifications in some regard. If we look at the Koppen climatic types, and I would show you this map here on the left, and then there's a description on the right of the different climate types. Basically, Koppen used these letters to delineate different climatic types. So, for example, let me just go to the North Polar areas, the Arctic areas, and you'll notice there's the initials ET, which stands for tundra climate, and EF, for example, over Greenland, which stands for a frost climate. If you see the letter H on the map on the left, that referred to a polar climate due to high altitude, okay? And that would be the H climate. And then there's other climates. The classification is all around. If I go to the Sahara Desert, the desert area of northern Africa, for example, it would be classified as a BWH climate, BW being a desert climate, and then the H referring to a hot climate, okay? So there's a wide variety of climatic types based on the Koppen climatic classification. A good portion of the eastern and southeastern U.S. is delineated CFA climate type, which is no dry seasons and hot summers. So this is really good stuff. If you get a chance, you may want to take a look at this on your own and do some really cool research on the different climatic types of the world. And again, climate refers to the type of weather we would expect for a location, and it's very important. For example, if you ever travel somewhere, let's say you take a flight to Australia and you want to know what the climate is of a location such as Sydney. You would want to look that up ahead of time because that will help determine what you're going to pack in your suitcase, right, to take with you. What type of temperatures does that location get? Does it rain a lot? Do I need to worry about getting wet? Those type of questions usually go through your head, and of course that changes from season to season. For example, when it's summer in the northern hemisphere, it's the opposite season in the southern hemisphere in places like Australia where it's actually winter. Okay, so just something to keep in mind how important climate is. Climate tells us the average weather for a specific location, and that's really the important thing. If you look at Trewartha's climatic classification, this is more of a breakdown for the 6 types based on Trewartha. Remember, 5 are based on temperature, 1 is based on precipitation. You'll notice the polar boundary column talking about temperature in a lot of cases. The dry climate type for Trewartha is bounded by the outer limits where potential evaporation, where you're getting that change of state from a liquid to a vapor is equal to the precipitation. So the amount of moisture brought into the atmosphere, overlying air, is equal to the amount of precipitation that falls out of the clouds in a dry Trewartha climate. Boreal climate, I'm just taking another example there, letter E under the climate group there. That's a 50 degree or above temperature for 1 month. That's the warmest month of the year according to a boreal climate type under Trewartha. All right, now we're going to get into some really good explanations as to why certain areas receive certain types of weather throughout the year. And this is delineated and really influenced mostly by what's known as climatic controls. Now, these are defined as the variation of the climatic elements, that temperature, the precip, and wind, from place to place and from season to season. We live on an Earth that is widely varying in different types of weather regimes or average weather you'd expect at those locations. There's 4 main climatic controls that we're going to talk about in today's training that's very important. The first one being latitude. Then we'll move on to a discussion of the land and water distribution and how that affects climate for a specific location. We'll talk about topography or the elevation of the land. And then we'll also talk about ocean currents, which are extremely important. Let's start off with latitude. Now, some refer to latitude as the most important climatic control. Latitude is going to refer to that position of the Earth relative to the sun. You look at a globe again, and you're going to see, how far north or south are you from the equator, from 0 degrees latitude? How close, are you living in a location between 30 and 60 degrees latitude? All right, that's going to help determine the number of sun hours that are going to reach your location each day. That's going to really determine the distance of the sun from the equator. How high in the sky does the sun get each day at your location? And it's going to vary throughout the course of a year. The angle at which those rays of sunlight reach the surface. The sun angle is going to be much greater, closer to the equator, as compared to, say, the polar areas. If I'm north of the Arctic Circle, then my amount of solar angle is going to be much weaker. It's going to be much lower above the horizon. Also, latitude, if we compare an equatorial area to that polar area, it really shows the importance of latitude as a climatic control. I mean, it's much colder over the polar areas on average as compared, let's say, closer to the tropical areas, the equator. Here's a great look. This is a comparison. The graphic on the left shows the winter solstice on 22 December. This shows the relationship of the sun, the amount of daylight hours that are received at various latitudes during the winter solstice is on the left. And you'll notice that the winter solstice, your most perpendicular rays of the sun are going to be shining down at 23.5 degrees south latitude, the Tropic of Capricorn, where you would receive about 13.7 hours of daylight. Now, as we move further south in the winter solstice on December 22nd, you'll notice south of the Antarctic Circle, south of the Antarctic Circle line, 66.5 degrees south latitude, you have 24 hours of daylight. But you also notice that the tangent, that sun ray, is going to be much lower above the horizon, even though there's 24 hours of daylight there in the South Pole during the winter solstice around 22 December. Now look at the differences of light, though. On the equator, on the graphic on the left, we generally have 12 hours of daylight. And then as you move north towards the Tropic of Cancer on the winter solstice, you only have 10.3 hours of daylight. And then if you go north of the Arctic Circle, 66.5 degrees north latitude, on 22 December, the winter solstice, you have 6 months of nighttime. The sun doesn't come up. Look at the graphic on the right. Now we're flipping it and we're showing you the way the sun's rays are aligned during the summer solstice around June 21st. If you look at the graphic on the right, notice the most perpendicular rays of the sun are now shining down 90 degrees overhead at the Tropic of Cancer at 23.5 degrees north latitude. And now the North Pole is going to be tilted or tipped towards the sun, where we have 24 hours of daylight north of the Arctic Circle, 66.5 degrees north latitude at the summer solstice in late June. Generally, the further north you go in the northern hemisphere during the summer solstice in late June, the greater the amount of daylight hours. Okay, so the amount of daylight and the relationship of the sun to the earth makes a huge difference as to where the most perpendicular the rays of the sun are shining at specific seasons, winter versus summer, as well as it's going to control the amount of daylight that is seen. That has a huge implication on the temperature. Now, if we move to the land and water distribution, we notice that land heats and cools about 5 times faster than water. And that's a fact. Land heats and cools 5 times faster than water. So now the location of the continents and the oceans is going to greatly influence Earth's pattern of air temperature, as well as the sources and direction of movement of air masses. So where are those land masses? Where are those oceans? That really makes a difference in the climate of an area. So for example, coastal areas assume the temperature characteristics of the land or water that is on their windward side. So, and I'll get into some examples here in a moment. The west coast of continents generally have oceanic temperatures, and east coast of continents have more continental temperatures. And you got to think about this. And I'm mainly focused on the mid-latitude area, the temperate areas, the temperate regions, between 30 and 60 degrees latitude, where the west coast of continents are going to have the influence of oceanic temperatures, because between 30 and 60 degrees of latitude, you generally have what's known as the westerly wind belt, where the upper level winds are going to blow from west to east. So if, for example, I'm located on the west coast of the United States, all right, I have a westerly wind predominantly year-round. And those ocean temperatures, which I'll get into more here in a minute, are going to have a huge bearing on my general average temperatures as well as my precipitation patterns throughout the year. Whereas the east coast of continents, I'm having the wind blow from west to east, and now I'm really going to be greatly influenced by what the air mass is upstream of my location over land versus the ocean. So temperatures with land and water distribution are determined by the prevailing wind flow. Now, the upper layer of the ocean, that's always going to be in a state of mixing, and that's due to the wind blowing over it. There's always going to be some type of turning of the water due to the wind, with heat losses or heat gains occurring at the surface distributed over a large volume of water. This mixing of that water sharply reduces the air temperature contrasts between day and night and between winter and summer over the oceanic areas. So you get less of a difference in temperatures if you look at the annual temperatures year-round at a place like San Francisco as compared to a place like St. Louis. Okay. Over land, there's almost no redistribution of that heat by turbulence. Thus, you're going to have over the continents much stronger seasonal and daily or diurnal contrasts in those interior continents. So if I take that same location like St. Louis, Missouri, in the middle of the North American continent, their temperature, average temperature in August may be, 86, 87 degrees, whereas their average temperature in the winter in January may only be like 38 degrees. So a much larger range of seasonal temperatures there because of the continent, being in the middle of the continent like that with very little oceanic influence, right? So during the winter over land, there's a large part of incoming solar radiation that's reflected back towards space by snow cover, whenever the solar radiation is reflected, it's a property that's known as albedo. And snow cover is very efficient at reflecting over 90% of incoming solar radiation back towards space. So you might have a sunny day with a nice snowpack. Generally, your temperatures are not going to warm up that much due to the albedo or reflectivity of the heat energy back to space. So generally, you get a big snowpack extending over large portions of the northern continents during the wintertime. That's generally going to result in the formation of dry polar air, that continental polar air. If you take a look at a previous video I made a couple weeks ago on air masses, that'll really break that down for you. All right, now the southern hemisphere. There's a difference between the southern hemisphere and the northern hemisphere. The big difference in the southern hemisphere is they have much less land and much more water as compared to the northern hemisphere. So if I were to look at the percentages, the northern hemisphere has 60%, the southern hemisphere has 60% water as compared to 40% land, resulting in more of a marine or oceanic climate with the absence of continental polar air. All right, so if you get this extremely cold air off the Antarctic continent, it descends from higher elevations and it comes down into the southern oceans. The trajectory of that very cold Antarctic air mass, okay, as it moves over the colder southern waters, that moisture is going to modify the air mass to more of a maritime polar air mass. So again, the amount of land versus water makes a big difference between the northern and southern hemisphere. Additional considerations on heating and cooling include the nature of the surface. You got to look at the color of the surface, the texture, as well as the vegetation. That's going to play a huge role in the overlying air temperatures. A dry surface is going to heat and cool faster than a moist surface. Plowed fields, sandy beaches, and paved roads, they become hotter than the surrounding meadows, those forests and wooded areas during the day. The situation is going to be reversed at night. So if I were to look at temperature for my particular location and I'm surrounded by a forest, I have a beach along the coastline, I could look at the differences in the temperature between the nearby forest and let's say that beach area. You're going to see a difference locally in the temperature. Now the distribution of water vapor, or the amount of moisture in the atmosphere, as well as the clouds, is also going to have an influence on air temperature. Areas with a high percentage of cloud cover throughout the year are going to have a high degree of reflectivity, but the energy which is not reflected is easily trapped in the lower layers due to the greenhouse effect. High moisture content areas have relatively higher temperatures overall for the climatic element of temperature. So let me just break this down for you. So if you have an area with a lot of clouds and a lot of low-level moisture or humidity, the air temperature really isn't going to change as much. It's not going to be as drastic, let's say, as an area that has a lot of clear skies and a drier air mass, less moisture in the air. So just want to make that known. Water vapor is actually one of those greenhouse gases which traps heat in the lower levels of the atmosphere. And you may have noticed this on a cloudy night, the temperature does not drop as rapidly, let's say, as on a clear night, because that cloud cover acts as a blanket and does not allow the long-wave Earth radiation to move back out into space. All right, so land and water distribution, well, a little bit more about this. The higher average temperature of the northern hemisphere is an effect not only of its higher percentage of land as compared to the southern hemisphere, but also the fact that its oceans are also warmer than those in the southern hemisphere. And this is partly due to those ocean currents, the movement of warm equatorial waters from the southern hemisphere into the northern hemisphere, caused by the southeast trade winds crossing over the equator. Additionally, the higher average temperatures in the northern hemisphere is due to the partial protection of the oceans from the cold polar waters and Arctic ice by land barriers. There is no such barrier between the Antarctic region and the southern ocean. So that's a big difference there, that we have that partial protection in the higher higher latitude North Pacific and North Atlantic due to that protection of the oceans from the cold polar waters and the Arctic ice. All right, let's move on to the next climatic control, and this is topography or elevation. This is huge. If you live in a mountainous area, you definitely know about this effect on your average weather over the course of a year. Climates over land may vary rapidly within very short distances because of elevation and the variations in the landforms. So topography or elevation plays an extremely important role in determining the climate of a region. The height above sea level exerts considerable influence on an area's climate. For instance, here's one great example. The climate at the equator, right, is 0 degrees latitude. You're thinking 0 degrees latitude, I'm in the torrid or the tropical zones at 0 degrees latitude at the equator. I should have hot temperatures year-round, a lot of humidity and moisture in the air. But no, if you live in the high Andes of South America, your climate is going to be much different than, say, somebody who lives at sea level. All right, so when we look at topography, we got to look at the general geography of locations on the Earth. The long, high chains of mountains, they act as climatic divides. These obstacles are going to deflect the tracks of cyclones, storm systems, and block the passage of air masses at the lower levels. And if the pressure gradients, or that change of pressure over a distance in the horizontal, if those are strong enough to force the air mass over the mountains, that forced ascent or rising air and descent or sinking air is going to modify the air masses to a great extent. So a location on the windward side of a mountain is going to be cooler and moist as compared to the climate on the leeward side of the mountain, which is going to be more warmer and drier climate. An orientation of the mountain range, that's going to block certain air masses and prevent them from reaching the lee side of the mountains as well. So that's very important. And we're going to get into a discussion also on the orientation of those mountain ranges here in a moment. If I were to look at the Himalayas and the Alps, they have more of an east-west orientation. That's going to prevent the polar air from coming in from the north and advancing southward. So if you're south of those mountain chains, the Himalayas and the Alps, you're going to have a milder climate in winter than other locations at the same latitude. So places like India and places in Italy, they're going to have a warmer winter in general, despite their latitude, because of the orientation, the east-west orientation of the Himalayas and Alps, keeping the much colder polar air north of the mountains. The coastal ranges in North America have north-south orientations. They're oriented north-south. That prevents the passage of unmodified maritime air masses to the lee side of the mountain range. The most noted effects of mountains is the distribution of precipitation, with precipitation values generally higher on the windward side of the mountain chain. Another great example of a north-south mountain chain in the United States would be the Rocky Mountains. So you get these descending winds off on the lee side of the Rocky Mountains, that's known as Chinook wind, and it actually can cause snow to melt rather rapidly, can cause really radical changes in the temperatures for a location, for example. This is a big factor in determining climate. Again, bottom line here, windward side of mountains are going to have a wetter and cooler climate as compared to the leeward side of mountains. So in regions where the prevailing circulation is going to flow against a mountain barrier, the amount of precipitation is going to steadily increase with elevation up to about 10,000 feet on the windward side of the range. Another important topographical feature is the presence of lakes. For example, the lake effect. It's notable for large unfrozen bodies of water. The Great Lakes are a great example of this. And that is a topographical feature. It's a water surface. And as that colder, drier air blows over the relatively warmer, moist Great Lakes area, it tends to pick up a lot of moisture in the low levels and deposit it on the lee side of the lakes, downwind of the lakes. So those lee side of lakes, they show considerable diurnal or daily and annual modification in the form of more moderate temperatures, but they're also going to have a lot more increased moisture, clouds, and precipitation, and increased winds. As wind blows across those Great Lake waters, it generally is going to have less friction, so it's not going to be slowed down nearly as much. Some of the biggest snowfall amounts occur downwind or the lee side of the Great Lakes in the wintertime. Lake Erie, Lake Ontario, if you're watching us tonight from there, you know exactly what I'm talking about as far as a lake effect snow machine and huge amounts of snow in the winter. Now finally, I'll talk about the ocean currents. This is a very important climatic control here at the United States, especially in Europe just as much. Any locations between 30 and 60 degrees latitude where the wind generally blows from west to east. These play a significant role in controlling the climate of certain regions. Ocean currents are very effective in transporting heat, moving cold polar water equatorward, southward into warmer waters, and then moving the warm equatorial waters poleward into cooler waters. These ocean currents are driven by these major wind systems, which are known as gyres, with cold southward moving currents flowing along the west coast of continents and warm northward moving currents flowing along the east coast of continents, resulting in cooler climates along the west coast of continents and then warmer climates along the east coast of continents. Take a look, no matter where you look in the world, look at all the continents, you're generally going to have a colder ocean current flowing along the west coast of the continent and a warmer ocean current flowing along the east coast of that continent. So let's break this down in the United States. Generally what we'd expect for a west coast climate based on ocean currents. And then we'll take a look at the east coasts. We'll run into that. And then we'll wrap up tonight's training. All right, so with west coast of continents, okay? The northern portions of the west coasts of continents are generally going to have cool summers and warm winters. Summers are cool due to the presence of these cold northern waters flowing along their shores. Winters are generally mild due to the transport of warm ocean currents to these latitudes. For example, the south and southeast coast of Alaska and the west coast of Canada, Washington, and Oregon have relatively warm currents flowing along their shores. These currents are known as the Aleutian and the North Pacific currents, which are branches of the northward flowing Kuroshio current. The southern portion of the west coast of continents generally have cooler climates than do the east coast of the same latitude. For example, San Diego and San Francisco, much cooler climates as compared to locations on the east coast of the United States, such as Jacksonville, Florida, or Norfolk, Virginia. So for example, that cold California current there, it's going to flow southward along the shores of California. That wind is going to blow from west to east over that colder California current, and you're going to have a cooler summer at that location. Now, due to the Pacific high pressure system, the winds normally are going to blow either across the cold current towards the shore, onshore, or parallel to the coastline. This results in cool air being advected or transported inland, allowing cities such as San Francisco to enjoy relatively cool summers. It was once noted, in fact, that the coolest winter I ever spent was a summer in San Francisco. Many people don't realize this when they make travel plans to these locations, such as San Francisco along the west coast in the summer. They're expecting it to be California. They're associating with warm beaches. Not necessarily the case. The water, due to that cold California current off San Francisco in the San Francisco Bay, it could be in the upper 50s to 60, 61 degrees, even in summertime. And you get that wind to blow in onshore over that colder current, and it makes things very chilly if you're down at Fisherman's Wharf in San Francisco, for example, on some summer days. Now, when the warm, moist air from the Pacific High moves up over the underlying current, you get extensive fog and stratus to develop. That's another thing that you typically see in the San Francisco area in the summertime. Lots of low fog, lots of low clouds and stratus because you're getting warmer, moisture air moving up and over that underlying colder ocean surface, that colder current. Another factor along the west coast is what's known as upwelling. Now, upwelling is a process by which cold subsurface waters are brought to the surface by the wind. And it's common when you have a wind that blows parallel to the coast. So what happens is the flow of air around the Pacific High is clockwise. It's going to flow parallel to the coast And then the wind's going to curve away from the coast, off California, for example, and it's going to take the top layer of water away from the coast. And from below, these colder subsurface waters come up to replace the top layer water that was pushed out to sea. And so you get this process known as upwelling. West coast of continents in the middle and higher latitudes are bordered by warm waters, which cause a distinct maritime climate characterized by cool summers and relatively mild winters with small annual temperature ranges. These are the upper west coast of the U.S. and Europe. Places like Seattle, Washington, has cool summers and relatively mild winters due to this. So it really depends where you're located at, whether you're in the lower latitudes on the west coast, the middle, or the higher latitudes, as far as the type of climate or weather you get. The west coast of continents in tropical and subtropical latitudes, so now we're lower latitude, are bordered by cool waters, and their average temperatures are relatively low, with small diurnal or daily and annual yearly changes in the temperature. Fog is common, not only in Southern California, but as well as Morocco, and these locations are also arid. Moving on now to the east coast ocean currents. Big difference here. In tropical and subtropical regions, warm ocean currents are going to introduce warm, rainy climates, especially on the windward sides of mountainous land masses. And as these warm currents move northward into middle latitudes, warm, moist air produces a hot, humid climate with frequent rain showers during the summer. Winters are relatively moderate, but still cold, along the coast due to the transport of warm water. And the higher latitudes along eastern shores normally have cold waters flowing southward from the polar areas. The region where the two currents meet, the warm current meets the colder ocean current, they usually have cool summers and cold winters with extensive fog where they meet, especially along the Grand Banks of Newfoundland and the Kamchatka Peninsula of Eastern Asia. And then the east coast and the tropics and the subtropical latitudes are paralleled by warm currents and have warm and rainy climates. These areas lie in the western margins of that subtropical anticyclone region. So places like Florida, the Philippines, and Southeast Asia are generally going to have very warm, humid summers with lots of rain year-round. And the temperatures do cool off somewhat in the winter, but it's not drastically cold by any stretch. The east coast and the lower middle latitudes, leeward of land masses, have adjacent warm waters with a modified continental type climate. Winters are fairly cold and summers are warm and humid. And then the east coast and the higher middle latitudes typically experience cool summers with cool ocean currents paralleling the coasts. So I talk all the time about in the weather discussions the Bermuda high, that subtropical high of summer. And you have a warm ocean current, the Gulf Stream current, flowing along the east coast of the United States. That acts to bring in a lot of heat and humidity during the summertime, lots of thundery, showery precipitation, and also influences the weather during the wintertime, the formation of these strong, powerful mid-latitude cyclones, these nor'easters, that has great impact on locations across the mid-Atlantic and New England. Right, and then the last slide here, the ocean currents are going to affect the location of those primary frontal zones and the tracks of cyclones. I don't think I have it now. I don't have a picture of this. I might need to hit that in the next training video. But off the east coast of the United States in winter, like I was just mentioning, you have two of the major frontal zones that are located in areas where there's a large temperature change or gradient. There's a large amount of warm water that's being transported into the mid-latitudes on the Gulf Stream ocean current, and the main hurricane tracks in hurricane season even in the Atlantic and Pacific Oceans also appear to follow those warmer currents, that warmer water. Extratropical cyclones, or those storms that form outside the tropics, also occur in warm waters in the fall and early winter. They really take and tap into the energy of the temperature contrast between the much colder landmass and that warmer water over these warm ocean currents. It could be a 40 to 50 degree change in temperature from just offshore the East Coast in the wintertime and the landmass of the East Coast, which really helps to energize the upper level winds and really get that cyclone to develop and intensify. All right, so that wraps things up for the training tonight. I hope you enjoyed it. This was on the climate. We talked about a lot of different topics tonight. from the climatic controls. We talk about climatic controls. Main points are the latitude, the land and water distribution, topography, and ocean currents. We also looked at the different climate classifications, the climatic zones, as well as these climatic elements of temperature, precipitation, and wind. The differences between the different climatology types, dynamic, descriptive, and physical. Looked at the definition of climatology as well. So I hope you enjoyed this training. We certainly hope you learned from the Spot On Weather team. In general, this is where you can find us right here. Find us on social media, Facebook, as well as Instagram and Twitter. For our Spot On Weather Weebly website, it's a great website. I definitely encourage you to check it out. A lot of great tabs. If you really love the weather, please check out the weather photo gallery. We do our 7-day outlooks updated regularly, as well as occasional weather blogs with a much more in-depth analysis of the upcoming weather. Thank you for subscribing to the Spot On Weather YouTube channel as well. I think we'll turn our attention to here shortly the general weather expected around the world. I've got the general weather that you typically would see in locations such as the Arctic. I've got that one lined up for another video here in the future. Going to be doing the winter weather forecast video as we get closer into the fall. Most likely the winter weather forecast video, what kind of weather we can expect for the upcoming winter. Looking at doing that in October timeframe. And there's a lot more exciting things ahead on the Spot On Weather YouTube channel with more informative, detailed analysis of the weather, including the very popular teleconnections discussions, the weekly teleconnections discussions, which I know I got a lot of good feedback last winter from a lot of you who really enjoyed listening to the analysis of the teleconnections and the type of weather we would expect for our winter season. So a lot of exciting things. Apologize, my voice kind of went in and out a little bit. Have to drink water at times to really keep things good. But overall, I hope you enjoyed the training tonight. Take care, everybody. Looking forward to putting more videos on the channel here in the future. Again, turn the Spot On Weather and these outlets and check out the latest forecasts and much, much more. All right, take care, everybody. I wish everybody a safe evening. I still got rumbles of thunder outside the Spot On Weather studio tonight. So it's one of the longer lasting storms I think I've seen here in this area for quite a while. All right, take care, everybody, and God bless.